Okay. Hello all and welcome to this session on DQN and reinforcement learning. My name is Shubha and I am an AI researcher at CellStrat with expertise in deep reinforcement learning. So the agenda for today will be, we will be discussing the DQN algorithm in reinforcement learning, and we will be learning how to apply it on one of the environments, and we will run a complete program end-to-end on CellStrat Hub, and we will see how the algorithm works in training an agent. So the audience here might be from varied backgrounds, so I'm not very sure. Some of you might be familiar with the reinforcement learning and some of you might be just familiar with the classic machine learning. So how we will proceed is, I will just give a very quick introduction or background on how reinforcement learning works, and then we will move on into the DQN algorithm. And once that is done, what you can do is you can create accounts on CellStrat Hub if you do not have an account. So we will share the link with you shortly, and we will be giving some time for you. If you have not created an account, you can go ahead and create an account and launch your workspace. So it is as simple as that. You just need to give your first name, last name, email ID, and create an account on CellStrat Hub. And I will be sharing the program with you as well, so you can upload the program on Hub and run the program. Once you run the program and you are able to visualize the output yourself, I will explain the different components of the program, and then we can, if you have any questions, I will help you understand the program better and how exactly RL works in kind of training such kind of an environment. So if any of you have any questions with the agenda that we'll be having today, or if you are expecting something, you can let me know. I will try to meet your expectations if time permits and if I'm capable of. So you can post on chat if you are looking forward for something from this session. I will try to cater to that. So with that, let's begin today's session. I am just sharing my screen. Okay, so here we go. I hope everyone can see my screen. In case you're having trouble, do let me know. So I will just begin with a quick introduction on reinforcement learning. So these many of you will be familiar with machine learning, and you would have learned some algorithms in machine learning, or you might be experts in machine learning as well. But then reinforcement learning works slightly different from our traditional machine learning approaches or machine learning algorithms. So you have your machine learning, within that you have your supervised learning, unsupervised learning, and then finally you have your reinforcement learning. So it works different from your supervised learning algorithms or your unsupervised learning algorithms. Over here, our main goal is to train a program, or what we call as an agent, to do a particular task. So the general architecture is, you have an agent, and this is the agent that you're supposed to train. And then everything around this agent comprises of what is called as the environment. Everything in and around the agent which it uses to train itself is called as the environment. Our main goal is to train this agent to do tasks correctly. So just to relate it to a real world scenario, how this is going to be is, you are trying to teach a child how to walk, or you're trying to train a dog or something like that. You give it rewards, you give it positive or negative rewards, and then by giving it rewards, it has to learn what is correct and what is wrong. If you're trying to teach a child how to walk, then you give it positive rewards of rewarding it with toys or chocolates or something like that. And then if the child makes some kind of a mistake, you frown upon or you try to scold, and then with the negative reward, it has to understand, or it basically learns that it is not supposed to do that particular action. So this is how it is divided. Everything in and around the child over here will be called as the environment. So it can be the reward that you're offering, it can be the chocolate, it can be the room where you're training, what exactly the child sees around the room, are there obstacles, all of these things which are surrounding your agent is your environment, and agent is the child over here, and what we are trying to train is the child to do correct actions. So at a very high level, this is how you frame a reinforcement learning problem. So tomorrow, if you have some kind of, if you want to frame a problem, if you take any real world problem, maybe something in supply chain or something like that, and you want to apply advanced machine learning algorithms to that problem, what you will have to do is you will have to frame it as in this way. You will have to create what is called as an environment. You will have to decide what is the agent. You will have to define what are the rewards, what are the actions possible, and so on. So with that introduction, I will move ahead with today's concept. So this is a very broad topic. As you can see, we covered the entire reinforcement learning course over 12 huge modules. It is kind of very advanced and it is extremely elaborate. But then I want to get to understanding DQN and the program quick. So I will just move on to, given this scenario, this is how a reinforcement learning problem is structured. Given this scenario, let us see how we can apply the DQN algorithm to train this agent. This is what is our ultimate goal. We are going to train this agent to do whatever we want it to do. So do tasks correctly.
So CellStrat offers that exhaustive RL course, the table of content Shubha was showing. This is offered as a very extensive course. It's a very advanced course. So reach out to CellStrat offline if you're interested in enrolling in this course. Today we'll focus on one specific module here or algorithm, which is Deep Q Network or DQN module 6 here. So yes, but it's overall it's a huge area. So each of these is very complex algo, and there's a separate course material on each of them. So okay, back to you, Shubha.
Yeah, thanks. Yes, that's right. You need basically, if you want to understand this completely, you need a huge background on all of these things. You have to understand it correctly. But then with the introduction that I just gave, you should be able to pick up with what is DQN and how it works. So these are some of the things that we will be looking at today. We will look at experience replay and fixed queue targets. I will be alternating between explaining this concept and juggling between this and code demo, because I don't want to make it very boring. So any questions anywhere, please do pause to ask. Okay, so over here, let's take a simple example. I will just take a simple grid world problem that many of us would have. This is kind of a maze. You would have seen some kind of games on TV where people generally play games of maze. So there will be some doors. You can just go in through those doors, and basically you will have to go to your destination. I will call this destination as G for goal, and this is your start point over here. So this maze here is pretty simple. You can have a very complex maze as well. So what happens over here is, now this is your entire environment, and then you have what is called as an agent. So the agent has to start from the start position. There will be some doors and the walls will be really huge over here. So the task of this agent is to get to the goal. This is our problem. So now when we have this problem and we want to apply RL to this problem, we will have to frame it as we will have to frame the problem as an MDP or something, so that you can use an RL algorithm to solve this problem. What happens over here is, these are all called as states. State 1, I will call this as state 1, state 2, state 3, and so on, all the way till state 9. And then there are 4 different actions that are possible at any given state. Let's say the agent is here. The agent can go in 4 different directions. It can either go right or left or up or down. So these are the 4 different actions that are possible, and S1, S2, S3 are the different states. State is something like the situation in which you are. So you can be in this situation, you can be in this situation, you can be in this situation. So those are called as states in the RL terminology. So I'll be referring to them as states in future. You have states, you have actions, and your target is to reach the goal. And now there is something else called as the reward. You will have to define what is the reward. The reward will be defined as -1. You will get a point of -1 for every step that you take. So you are here, if you take a step and you go here, since you took a step, you are going to get a reward of -1. And if you somehow manage to reach the goal, you will be getting a very positive reward of, let's say, +10. So this reward has been defined. Action has been defined. There are 4 actions, up, left, right, and down. And state is also defined. There are 9 states over here. So what the Q-learning algorithm does is, all of the states are lifted. It creates a matrix basically between the states and the actions. So all of the states will be listed something like this, all the way up till S9. And all of the actions will also be listed. I will call it as A1, A2, A3, and A4, or it will be up, left, right, and down, whatever. And for this is a matrix of size 9 cross 4, and for each of these a value will be calculated over here. For each of these we are going to calculate a value. How are we going to calculate the value? That is what is called as the Q value, and I will be sharing the formula shortly. We will use a formula that is available, and we will calculate the Q value for every state action pair. So for every state action pair, we will calculate the Q value, and that way we are going to populate this entire table. And once we populate this entire table, this table, we will be using it as a cheat sheet or some kind of a reference table. So now let's assume that all the values are populated over here using a formula which I will share shortly. Once you have this reference and you have this table, what we will do is you can just refer to it. So for example, let us say an agent is playing, the agent is somewhere over here, S1, S2, S3, S4, S5, S6. The agent is somewhere over here. When it is at S6, it will check out the value for the different actions. What are the values for each of these actions? And whichever action has the highest value. So let's say this was 4, this was 3, this was 8, and this was 2. So whichever value for this state S6 has the highest value, it will perform that action. It is going to perform that action. So this is the basic idea between our Q algorithm, or calculating the Q value. Q learning is nothing but the algorithm which is based on this idea. So with this introduction, let's review the Q learning algorithm. So what you will do is you will train the program for several episodes. So an episode is nothing but you start from scratch until you terminate. So when will you terminate? You terminate when you reach the goal. When you reach the goal, we can terminate, or we can also say if you get stuck somewhere, you're going in loops and loops, you're not going anywhere in the near the goal, we can say terminate if you can't find your goal in 20 steps. So this is something like a game. So we are playing chess, you finish the game, an episode is completed. So that is something similar to that. So when we are training, we will train it for a large number of episodes. We have a lot of episodes over here. Let's say some 100 to 200 episodes. And for each episode, what we will do is we will use this formula over here to calculate the Q value and populate the matrix which we saw in the previous step. So the Q value at any given state for a given action is populated as whatever was the current Q value. And when you performed this action at that particular state, you got a reward. You got a reward. And after you performed an action in that particular state, you moved on to the next state. You moved on to the next state called as S dash. You were in state S, you performed an action A. Because you performed an action A, you got a reward R. And you also moved on to the next state S dash. And using the same policy, if you perform another action A, that is the Q value at the next state with that action minus the current Q value. So basically, this is the update formula which I just discussed. So moving on to our grid world, if you are in one particular state and you take an action A, if you perform this action A, you go to the next state S dash. This will be your next state S dash. And in this S dash, using the same policy, you will perform another action A. So when you perform that in the next state S dash, whichever action has got a maximum value, max of the Q value in the next state, that minus the current Q value. So you will repeat this multiple number of times until you reach your goal. So this is basically our Q learning algorithm, and this can be, once you have this formula handy, it is very simple to code it using Python. So in the previous module, we would have discussed more in detail about the Q learning algorithm, and we have coded it in Python. It will be pretty simple. We can just create a dictionary or something like that to populate the Q table. But you would have already realized that creating such kind of a matrix is possible only for small state spaces and small action spaces. In a real world problem, if your state space is really huge, you will not be able to do it. It is kind of not possible to create such kind of a matrix and populate it using simple Q learning algorithm. So yeah, the limitations have been told over here. In the year 2015, DeepMind had this problem that it's not possible to extend Q learning to real life problems. When they came up with this idea of using a neural network to compute that Q table, they came up with this idea of using neural networks, and they implemented it on Atari games. So all of these Atari games, you can just create environments for them using Gym, which I'll be showing shortly, and then you can use deep learning over here. They used deep learning. They built a convolutional neural network because all of the Atari games were in form of images, and then they used deep learning to train all of these things and create the Q table, and then they got state-of-the-art performance for all of the Atari games, where the program was able to surpass human level of playing of these games. It was kind of a breakthrough. So yeah, here is what we just discussed. You have states and you have actions. You build a Q table, you calculate the Q value. This is the simple program which you can implement using Python. But then today we are discussing DQN. So in DQN, what happens is you have a black box, which is your neural network basically. You pass in the state and it gives out Q value for all of the actions, for the different actions that are possible. And you choose that particular action which has got the greatest Q value. So with this introduction, I think we can just get to the code and we can understand more about how how can we create an environment, or how is it possible to create environments, and look at some of the environments on in our program in CellStrat Hub. So any questions with what was covered so far?
So some real business use cases could be such as a mutual fund portfolio, right? So when to buy what stock, when to sell what stock in a mutual fund, right? Or planning your supply chain for retail products, right? So when should factory produce more products, and when should the store trigger more orders to the factory? So there are some very interesting use cases of trying to create a right policy. So just to create some context on that, and also gaming, of course, all kinds of games can use reinforcement learning. Any other questions by audience?
Okay, I see one question here. What is the alpha variable in the Q formula? Alpha is the learning rate. So the formula that you just saw there is the learning rate over here. So you have your reward plus gamma times maximum of Q of S dash minus Q of S of A. This entire thing will be your error term, and by how much do you want to have that? It is basically your step size. Of by how much do you want a part of that error to be used while updating your Q value is what is alpha. And gamma over here is called as your exploitation rate. So a lot of pre-work is necessary for RL algorithms. So basically how this works is, initially your Q table will be populated with zeros, and then you just let the agent to randomly explore the place initially. Okay, initially what it does is it doesn't know anything. Okay, when I drew my grid world, I knew that this was a grid world and there are mazes, there are doors. I know a lot of things. But when a computer does it, it absolutely has no idea about anything. So what it does is it explores the area a bit, and once it is kind of familiar with what action gives it more reward, what is the action that it is supposed to do, it starts exploiting. So gamma over here is your exploitation variable.
So there are some more questions also.
Shubha,
Yes.
can you hear me? Good morning. This is
Yes,
Krishna
yes,
here.
yes. Hi, Krishna. Yes.
Hi. Can you please go back to that screen where you are
Yes,
showing the
sure.
formula?
Yes, sure.
So here on the left side, there is a new Q value for that step and for that action. Is it?
Correct.
And S
So
dash.
what, S dash is the next. Okay, S dash is the next. Sorry, I'll just go back to that screen. Yeah, here. Okay, S dash is the next step into which you go to. Okay, let me just draw the grid again. So this is your grid. You start at one particular point. Let's say your agent is here. So agent is at state S1. Okay, this is state S1. Let's say the agent is at state S1. It performs some action. Let us say that it performed the action of going up. So I will go up. I performed an action of going up. When I go up, I go to state S4. This is S1, S2, S3, and S4. I go to state S4. So S dash is the next state that you go to when you perform action A. So let me just read through it. Choose action A and S from the policy derived from Q, which is epsilon greedy. Epsilon greedy policy over here means it balances between exploration and exploitation. Exploration will be initially it is just a random policy. It is just trying to explore this grid. So initially it's all random. Later on, it will exploit what it has learned. So using an epsilon greedy policy, it will randomly explore. And once you take action A, once you perform action A, you will get a reward. Observe that reward and also observe S dash. So observe the next state into which you are going to. So observe the reward and observe the next state S dash. So in the next state S dash, choose the best action. Max A Q of S dash comma A is the best action in the next state S dash. So in our scenario, next state S dash is going to be S4.
Okay.
So
S4.
choose that minus the current Q value at S comma A.
And we are updating that with the current value, is it? And you are updating that
to the current value, you will be adding it. So this current value plus you are adding something. Every time to the current value, you are adding something. Initially, we will randomly initialize this table to all zeros. Initially, we randomly initialize the Q table to all zeros. And once you do that, you gradually update it. So it is, if you look at this formula, reward is the one that is ruling this formula. So reward is the one that's ruling. So when you gradually update, if you're doing a wrong action, you would have, your system will be in a place to say it's negative reward. So if you're doing a wrong action, it will all have low values. But if you're doing a good action, reward will have a high value. So eventually this table is, since reward is the ruling factor of populating this table, eventually it will
where does the reward
have
come
a
here?
good
Where is
set
that?
of values. Over here, you have the R over here. R is the reward that you get for performing that action.
Okay.
So yeah, I'll give a very real life scenario. So I moved from US to India, right? And then every year, me and my family have to plan our vacation schedule, right? Now the question is, should we go to Ooty first, or should we go to Chikmagalur first, or should we go to Rajasthan first, right? Now, so the reward is measured in a sort of a satisfaction score. So every year we try a different vacation schedule, going through different vacation spots throughout the year. But after 5 years, so 5 years worth of episode, then we discover, okay, the most highest satisfaction is derived from first visiting Ooty and then Goa and then Rajasthan. You see the scenario? So, so by iterative hit and trial, by many episodes over many years, we discover our perfect, most satisfying, the vacation, itinerary. So that's what is we are modeling here basically.
Okay. Thanks, Vivek. So my question is, how does it R will be known after moving the step, right?
No, after performing the action, yes, you will know R. So initially it is exploration. So after you perform only, so if you're going to a restaurant that you don't know, you're exploring the city, you're new to the city. So you just try out a restaurant. Okay, you will say, okay, fine, let me try out this restaurant. So the reward you will only know after eating there. You learn by making mistakes. You learned that fire is hot only after you touched it once. So that is the way it learns.
I mean, same thing in the stock sales, right? In the when I'm buying and selling shares in the stock market, the same scenario applies, right? Which stock, when, how much, right? And given my budgetary, so we model various scenarios to find the most optimal policy and maximizing the return on stock investment.
Right. Here, where is it R calculated? That is what my question is.
Okay, no, R comes with the environment. R is not calculated. So this is there is this.
Vivek, this is Swami. If I may, I'll just give you an illustration. Just correct me if I'm wrong. So, for example, if you are trying to do a last mile delivery of different packets, and typically, imagine a Dunzo environment, the reward could be in terms of the savings of the overall kilometers. So you assume that delivery person has to travel 200. The savings could be the reward objective, and he has multiple options going to delivery point one, picking up from the pickup point 8. So there are multiple combinations, and based on this you will arrive at the maximum savings are, and you will be able to use this
Correct.
functionality to determine
Precisely
the
correct.
maximum savings.
So Zomato and Swiggy delivery boys also use RL techniques. So Zomato and Swiggy delivery boys also have to optimize their route behavior based on minimizing the fuel cost but maximizing the deliveries of Zomato and Swiggy, because it depends on how you optimize the route, right? Minimizing the travel cost but maximizing the orders delivered and the value of orders delivered. So you got it right. That's right. So there are so many scenarios this is being applied. Even Ola and Uber cab optimization. Should I keep more cabs in Kormangla or should I keep more cabs in Sarjapur, right? So those things are being optimized with reinforcement learning by Ola data science team. So there are so many use cases. That's why it's so important. I hope that helps some of the questions.
Yeah. So is R constant here? That is what my question was. Or is it going to be changed? Are you going to change it with time?
No, R is constant over here. I think Krishna asked a question on how R is defined. It all, if you remember, I'll just go back to my first, over here, the environment. This environment is what you have to define. Somebody has to define the environment to you. So what does the environment consist of? It consists of all the states. So states, in my case, whatever grid world I wrote, I have 9 states, S1, S2, all the way till S9. And actions, 4 actions I have, A1 all the way till A4. And reward also has to be defined. If you take till every, how do I define? Every step that you take, you will get a reward of -1. But if you reach your goal, you get a reward of 10. This is how I design my reward. So the environment is predefined. This is the environment that is given to the program. And once this environment is given to the program, this agent has to learn how to play or how to navigate through this environment. So this is similar to chess. It's like when chess is given to you, all the rules of the game are told to you. This is how the bishop moves. This is how the night moves and so on. Everything is told to you. What you learn is how do you navigate through the entire configuration in order to maximize your reward, which is winning. So that is what
Yeah,
you do, but the rules are given to you. So everything is predefined. You have to learn how to navigate through the environment.
Okay. Thanks, Shubha. So
Okay.
that is clear. So
Yeah.
now here, your next action is calculated. I mean,
Mhm.
given that you are in certain state, the next
Mhm.
action is chosen in such a way that the reward is maximum, right? You will get. You will get
Initially, this formula, this one thing that I want to say here, Krishna, is this is heavily dependent on the previous modules over here. So I'm trying to give an intuition of how this works.
Yeah.
Since it's heavily dependent on the previous module. So you, for this session, if you are new, you can take into consideration that it is this reward which is kind of ruling how the Q table is populated. So reward is the main ruling factor over here. So
Understood.
that is what is matters over here.
And in the example you gave, -1 and 10, that can be, for example, it can be 10 and 100 also, right? You reach the
Yes,
goal, you
that
will get
can vary. So when you, before you
right? That can,
define the environment, yes, you can vary. Yes.
okay.
So why I have given a negative number is, why have I chosen a negative number is, I don't want my agent to keep going in loops. So if you say
Okay.
10 and 100, what happens is, this is your agent, it goes all the way round and round and round and round. So in some 10 rounds, it is going to get more reward. So if you reach the goal, you will get 100. But for every step that you take, if you are getting 10 points, then you get stuck in an infinite loop. You will get more reward than reaching the goal. So
Got
that
it.
is another question altogether, where when you are creating an environment, how exactly, if you do not design the rewards correctly, you might, the algorithm might not work. So it's extremely important on how you define the environment. So that generally happens with a lot of discussions with a subject matter expert. Like if you're doing a supply chain, then you will have to talk with a subject matter expert, understand the problem and design rewards.
Okay. Yeah, that explains. Thanks, Shubha. Yeah.
Sure. So let's move on to the program for a bit to understand our environment and what exactly are we trying to do over there. So I would request everyone to log on to cellstrathub.com. So all that you have, I have logged in before getting into the class today. So just all that you have to type is type in cellstrathub.com. And if you already have an account, great. Otherwise, you will see a sign up option over here. It does not ask for a lot of information, just your name and your email ID. So you can just put in your name and email ID, sign up, and you can start using the workspace for today's class. Also, the other lot of packages which are available with CellStrat Hub is what you will be seeing over here. Into my account, I have all of these packs that I have added into my account. So based on your interests and preferences, you can add whatever packs that you want into your account. But you can do that later today. But for today's class, I will be sharing the program with you shortly. So just if you have not signed up, please do sign up.
Ma'am, I have one question regarding the packs.
Yes.
If I have installed packs, they occupy a lot of space, so the storage is huge. Is there any way that we can uninstall any pack if we are not using it?
So
Yeah,
Vivek, will you?
yeah, Vaibhav, you can just you can show rm-r command in the terminal, Shubha. You can show, you can open the terminal and show rm-r, and Vaibhav, contact us offline. We will manually also delete the pack from your account in the backend database. But for the short term, you can execute what is called as rm-r command, delete an entire folder, a pack, basically.
Okay, sir. Okay, thank you, sir.
So like here, no, don't do that, Shubha. You'll lose
No,
all the
I
packs.
just typed it. No, I just
Uh-huh.
typed it. I'm not going to do
So
that.
RM, you open the terminal, rm-r, the folder name, it will delete the entire folder and its content. So careful. And then later on, the problem is just the deleting here will, what it will do. So if you shut down the instance and restart it, the pack will come right back, consuming space again. So you'll have to contact us offline so we can also delete it from your database row later on. So it will not come back after you restart the instance.
Okay, sir. Yes, sir. Thank you.
Please don't check out all the packs.
Okay.
Your free tier will fill up quickly. Only check out the pack you are interested in working at the moment, because you have 8 GB space in the free tier.
Yes, sir. Sure, sir.
Okay, so let's move on. Is everyone done with logging into CellStrat and launching a notebook? You will just have to click on Launch Jupyter Lab, and then yeah, you should get the screen. I will just share the notebook, and then you can just upload the notebook that we will be explaining today. You can execute it and look at the output for yourself. You can execute this. It will be fun to see that. So just all that you have to do is upload file and load this program, which will be shared with you. So Vivek, I will just post it here.
You can post the Google Drive. So we'll have to upload a zip file here. Is it a one file or zip file?
It is just a one file that I have.
So we can upload, download and upload one file, share it. No, you can, yeah, send it in the chat here.
So here is the program. Download the program from this location and download the program from this location and upload it on Hub in the main folder itself, or you can just create a simple folder like DQN using RL, and then you can just upload this program. The name of the file is dqncardpool.ipyng. So this is here. You can just download it to your local system and upload it on Hub.
I hope everybody was able to create a Hub account. So you have to create an account on CellStrat Hub, because this program has been tested and certified on CellStrat Hub only. So I'll send the link again for those who joined later. You can go to cellstrat.com or cellstrathub.com. Both lead to the same point. So you create an account if not already there, and then sign in after you verify the OTP sent to your email. Then check out the RL pack. Then you can start the workspace, go into Launch Jupyter Lab and upload this program shared through Google Drive. The Google Drive link is also being sent again. Only one file, it's an IPYNB file.
If this is done, shall we proceed? Please let me know if you need some more time. I can wait for probably 5 more minutes. But if you are done in the interest of time, please do let me know so that I can proceed with the program.
Where is everybody so far? Just write done if you have been able to upload. So it's recovering data for those. So in 7 days, it backs up the data to an S3 backup to preserve space and reduce AWS cost for CellStrat. So just wait for a few minutes. It will recover your data from S3 backup and you will be able to launch it. So if you're actively using it, it won't back up, but 7 days of inactivity means it will create a backup and it will do data recovery next time you log in. Please write done in the chat if you have been able to upload the file to your workspace environment. Please write done in chat. Okay, many folks are getting done here.
If we are waiting for it to launch, in the meanwhile, I will just explain about the environment. So basically, OpenAI is the organization which has come up with a lot of environments. So you can just go to gym.openai.com just to have a look at what are the environments available. And they have a lot of environments that are available where you can practice RL problems, like you can implement different RL algorithms on all of these things. So what you mean by it is creating an environment. So I just now told that I just drew a simple grid, that is, you just move from start to end. When that is the case, you will have to provide everything, all the rules and the environment to the program that's trying to learn, which means you'll have to tell what are the states available, what are the actions available, and how are the rewards defined. All of these things you have to give the information. So once you give, we will use an RL algorithm using all this information to learn how to navigate through the system. So creating an environment itself is a challenging task and it might be difficult. So what we do is we use the environments which are given by OpenAI's gym environments. And today in particular, we will be looking at this cart pole environment. So cart pole environment is balance a pole on a cart. So we can click on that and it's going to give us an explanation. So this is simply a small cart that you have and a pole is standing on top of that cart. So you can just imagine, you would have played this game of you just try to balance a stick or something on top of your hand. So this is very much similar to that. How long will you be able to balance it on your hand? How long can you balance an object on your hand, on your head, on your nose, and all such things? So this is the problem statement, and the environment has also been defined for us. All that when you are balancing a stick on your hand, what do? You either move left or you move right. You move your hand left or right so that it stays in place. If it's about to fall off, when you're trying to learn how to ride a bicycle or something, your handle just keeps moving left and right until you're able to balance it correctly. So that is exactly the actions that you will take to balance this cart pole. So the actions that you will be taking is move left or move right, which is told over here. The system is controlled by applying a force of +1 or -1 to the cart. And if you look at the source code, which is available on GitHub, and you kind of scroll down, the details are nicely documented in Gym. This is the environment that they have. See, you can see that they've created a class cart pole environment, which is a base class of Gym's environments. The actions, they have told it nicely. It is a discrete set of actions.
Sorry, ma'am, can you zoom in a little, please?
Okay, yeah, sure.
Sorry, thank you.
Yeah, sure. Is it better now?
Yeah, this should do. Thank you.
Okay, yeah, sure. So the actions that you have over here are 0 and 1. 0 would mean push the cart to the left and push the cart to the right. And then you have a reward. Reward is +1 for every time step taken. So over here, reward is simple. +1 for every second or every time step that you are able to successfully balance the pole. So if you're able to balance it for a long time, like 10 time steps or 20 time steps, you will get a reward of 20. Whereas if you just balance it for 1 or 2 time steps and the stick falls off the cart or it falls off your hand, then you just get a reward of 2. So the reward is defined that way. A reward is 1 for every time step taken. And the most important part is the observation or your state space. This is a vector of 4, where you have cart position, you have cart velocity, the angle of the pole, and the angular velocity of the pole. So it is basically every state. What do you mean by every state? Every state is every situation that you are in. If you are in one particular situation, what is the action that you will take? Will you move left or will you move right? Let us say that the cart is in the center position and it has some kind of a velocity, and the pole's angle, let's say it's 45 degrees right. So which means it's almost falling off. If just imagine a pole on your hand and then it is tilted 45 degrees right, which means it's almost falling off. In order to balance that pole, what you're going to do is you'll move your hand to the right. So when you move your hand to the right, you will somehow try to balance it so that the pole does not fall off. So the pole angle and the pole's angular velocity. Every state over here will be a vector of 4. Every state is going to be a vector of 4 with all of these things. And this is how your reward is there, and episode terminates. So if the pole angle is more than 12 degrees, so I just gave an example of 45. At 45 it definitely falls. So if your pole angle is more than 12 to the right or minus 12 to the left, it is going to fall. And if your card position should also be in the center, if it kind of goes too much to the right, it might fall off the cliff or something. And you have to, at the max, you can balance it for 200 time steps. And if you're able to get a score of 190 or 195, it means that you have solved it. So this is an overview of how the environment has been defined in a pole which is attached to an unactuated joint to a cart which moves along a frictionless track. So this is the description, and you can always, you're welcome to look at the gym page once the session is over today. All that you have to do is OpenAI's gym environments, and you have classic control, and you can look at the cart pole environment. They have a very detailed, nice description that they've put up there. Okay, so this is our environment. All of these things are predefined. State is defined, action is defined, reward is defined. Now we have to train a program which learns how to balance a cart pole. So what we are going to do is, let's look into our program. I will go all the way up till creating the environment. And once that is done, let's move on to our PPT to understand how the DQN, deep learning or DQN works, and then we will come back and execute this. We import some libraries, and this basically is just for visualization. We can train this without visualization, but it would be good to have a visualization. So all of these things, what you see over here, are helper functions for visualization. What we are more interested is here. You have to import the package called as gym, and you make an environment. So you create the cart pole environment. Once you create the cart pole environment and you reset it, it will be in the start state. So reset is nothing but in the chess, the start state is the reset state. Once you finish your game, you will rearrange all the pawns, however it has to be, like 2 rows of black and 2 rows of white. That is basically your reset. And you just reset that, and then I have just printed it. So when you reset, it's all having some values where the pole is straight. So this is what we are interested in. And if I just go up over here to
the 4 values represent the current state of that pole.
Yes, that's right. So 4 values are giving those values which we saw, which was pole velocity, pole's angle, position, and I'm not able to, I think the angular velocity or something. Yeah, whatever we just saw, those are the 4 things.
So for uploading the file to CellStrat, there's an upload button. Shubha, you can show the upload button.
Yes, here you have an upload button. You can create a new folder, or you can have it in the same folder also. Here is an upload button. Just click on that, and once it is on your local system, once you have downloaded the program to from Google Drive to your local system, wherever it is stored, just you can upload it there. And we are creating the neural network using PyTorch. So you can select the PyTorch kernel if it's not already there. So you just click on this and you can select your kernel, PyTorch 1.9. This runs on PyTorch. You can select the PyTorch kernel. Okay, and this is again a helper function, which I will not go through. This is to get this rendering. So this is to get this rendering, which I just want, which we just wanted to display on the screen. So I will not go through that. And over here, now, what is our goal? We have to train the pole to balance on top of the cart. That is the goal that we have in mind. So what we are planning over here is, we will pick some random policy. Just take some policy, create a policy. What is a policy? Policy is nothing but what is the policy that you are going to use to train to balance the pole on the cart. That's the policy that we have. So the random policy that we have over here is nothing. If angle is less than 0, we will choose action as 0. Otherwise, we just choose an action as 1. So for every given state, these are all the different states. We have okay, maximum time steps is 200, that is allowed. So for around 200 time steps, if the angle is less than 0, we will choose action as 0, and if the angle is greater than 0, we will choose an action as 1. And once you do that, you will perform that action. This ENV is nothing but your gym environment, and step means perform the action. So the action can be either move left or move right. When you perform that action, you will get a new observation or a new state. So you are in a particular state and you randomly chose some action based on some random formula that I created. This is just a random formula. We have not yet got to our algorithm. You perform that action and you get an observation rewarding done. Done says whether the episode is completed or not. And once that is done, there is a visualization over here. So this visualization is just going to help us visualize this is going to help us visualize running of this cart. It just falls off because this is very random, this is not a good policy that we have chosen. Within just a few time steps, it is going to just fall off. So is everyone along with me up till here? Please let me know if I'm kind of going fast. You want me to slow down or something like that? Are we clear on the environment?
Ma'am.
Yes.
So, like those 200 steps, if we are not able to achieve the desired target, then it will restart again by resetting.
Yeah, whenever it falls off, it restarts again. So we will you can define number of games you want to play. So let me say I want to try balancing it for 20 times. Okay. So first time I will try, it falls off. Maybe it balances for some 4 or 5 steps and it falls off. You try it second time, you balance it for some time and it falls off. Then you try the third time, fourth time, and so on till 20 times.
Okay.
So you try it all the way for 20 times, and then you can define how many times do you want to play. So yeah, so it is something like that. Yes.
Hello, can I?
Yes, sure.
So is there any other the policy that you have defined is to make the pole at 0 position?
Yes,
is that very strict? Is that very strict policy?
This is just for demo purposes. I just wanted to show you can use any policy. You can say if position is less than 0, or you can say if position is less than 100. Just a random policy. This does not mean anything. I just wanted to show you how it works.
Okay.
Can you also please? Yes, sure. Go ahead. Sorry.
Yeah. Can you also please brief about that environment gym?
Yes. So yeah. So basically, you just go to you just say. I'm sorry. You can say OpenAI gym environments because OpenAI is the organization and they came up with gym on all of these environments. So over here, I just did OpenAI gym environments, and these are some classic control environments that they have. Like this is what we will be working on. Probably after today's class, you can go and try it out on some of these other environments as well. Like this is mountain car. It has to go all the way till this flag that you see over there. So you can try out this algorithm on other environments. Today's class, we will be doing card pole. There are other environments that are available. So basically DeepMind trained it for all of the Atari games, and Jim is in fact helping us. It is given all these environments to us so that we can use it to try if our RL algorithms will work on these things. So you can try on any of these Atari games. You have to just create whatever is the name that's given over here. Sorry, Carnival-V0. That's the name of the environment. Just create that environment. Look what are the actions available. See what are the states available. How is the rewards defined and all of those things. And you can do it. If you're looking at an explanation specific to card pole, yeah, then card pole. The state space is a vector of 4 things, which is card position, velocity, pole angle, and pole's angular velocity. The actions that are possible are just 2. You just move the card left or right since you're trying to balance it. And reward is 1 for every step taken. So if you're able to successfully balance it for 100 steps, then you'll get 100 reward. So maximum is 200. So if you are able to successfully balance it for 200 steps, then good. You have trained it. You have trained your program. So is this fine? Shall we move ahead?
Yes, thank you.
Yeah. Okay, so as we saw, this was the equation that we are trying to update. We have a new Q value. We will update it with the existing Q value and alpha times learning rate times the reward that you get plus gamma times the maximum Q value at the next state minus current Q value. Over here, the loss function is going to be the current Q value that you already have minus the expected Q value that you will be getting, the next Q value that you will be getting. What is the difference between the 2 Q values? Square. So this is nothing but it is similar to our mean square error, which we would have seen in supervised learning. So it's just a simple mean square error loss. What is the current Q value at any given point and what is the next Q value that you have at any given point? Minus all of those things and square of that is your loss function. Okay, so there are 2 important concepts that are related with DQN. First one is called as experience replay and second one is called as fixed Q targets. I will explain what is experience replay first and then I will go to fixed Q targets. So what this does is it begins by learning an environment. Okay, it begins by learning an environment. And in this environment, if you have, what happens is if you pass experiences. So now let us say agent is in state S1 and then this agent goes to state S2. This agent is in state S1 and then it goes to state S2. So in state S1, it takes an action A, then it goes to state S2, it takes another action A. So these states, since they are very near to each other, they will be highly correlated. And we do not want this correlated data to be passed together as input into our neural network. So what we will do is, we will collect some number of states or some number of experiences and we will put all of these experiences in a huge buffer. So the length of the buffer ideally will be around some 1 lakh or close to that. We will put all of the experiences in a buffer and we are going to shuffle all of them. So when we shuffle all of these experiences, once you will get a state S1 and you will decide what is the action that you have to take. Next, you might get state S8 and you might have to decide what's the action that you want to take over there and so on. So if you're trying to play a game or something of chess, like initially you make some moves and you just keep learning what has to be done initially. You might not move further. So you might learn, okay, if this is your chess board and first row is arranged and second row is arranged, over here also first row and second row are arranged. If it only kind of learns what happens in these first initial rows, like if the chessboard configuration is all random, it might not get to there. So what we do is, we take different configurations of this board, lot of different configurations, say 1 lakh configurations, and put it in a huge buffer, shuffle them, and these states will be given to our algorithm in random order, which are all shuffled so that our algorithm learns better. So this concept is called as experience replay, and programmatically it is very simple. What we will do is we will just create a class, an experience replay buffer class, which will kind of shuffle this. So moving back to my code over here. Yes, here is the replay buffer class, a fixed size buffer class to store experience tuples. So if I just scroll up slightly, yeah, buffer size has been defined over here. Buffer size has been defined, which is huge and which will usually be around 1 lakh or 10 lakh. The buffer size will be defined, and that is the buffer size that a huge buffer is going to be created, and all of these experiences will be stored in that. So what do you mean by experiences? The action, the experience is basically nothing but the state. In that state, what was the action that was taken? What was the reward that you got? What is, once you perform this action, you will get a next state. What is the next state that you have? And done tells you whether it was terminated or not. So all of these things will be stored in what is called as an experience, on and on. So for the training will not happen until like some 1 lakh of these experiences are stored in your experience replay buffer. Like there's a method add to add all of these experiences into your buffer. And when you want to extract out of this buffer, like when you want to sample out of it, all that you have to do is random.sample a batch size. So basically in deep learning, the training happens in mini batches, and a mini batch size will be defined, and we will get a mini batch size out of that in order to train. So the mini batch size is also defined, but the batches that you get, unlike our normal deep learning methods, will not be in sequence, but it will come from these set of experiences. So this is an important concept that DeepMind brought into while they were training Atari games, and this is implemented in code in this fashion. Any questions here? Also, some other points that are there over here is some state action pairs are very rare to occur. So all of these things will be stored in an experience replay buffer. So if you can iterate over this buffer multiple times, the idea is you will be able to learn better. Also, you can give high priority. Okay, I'm not discussing priority in today's class, but it is possible to give a different priority to these rare occurrences of state action pairs. So if that is possible and you store it in an experience buffer, it's going to help us. The other important concept that DeepMind introduced is what is called as fixed Q target. Okay, we need to kind of pay attention over here to understand this clearly. What happens is, this was our update formula that you're having. Your Q value is updated with the existing Q value plus the reward that you got plus gamma times the maximum Q value in the next state for the next action minus the current Q value. So if you look at this, you have a particular policy. You're using that policy to calculate the Q value. You are also using the same policy P to calculate the Q value in the next state. So you have a state, you calculate its Q value, it goes to the next state. In the next state also you use the same policy to calculate your Q value. So if this moves in the sense, if this gets updated, this also gets updated. So what happens over here is, this is trying to get closer to this, but then this is also moving. So it kind of becomes like chasing a moving target problem. We are trying to get our Q value close to this value, but this itself is moving. So we are trying to get our Q value close to what is called as a target, but the target itself is moving. So if you're trying to shoot, it is easier to shoot a stationary target, but if your target itself is moving, it becomes a chasing problem. It is not possible to get near to a moving target. And in order to solve this, what they did was, you have one neural network You have one neural network which calculates this Q value. Okay, let me call that as NN1. And you have another neural network NN2 which calculates the target. So this is basically your target. You have another neural network which calculates your target. This is your local neural network and this is your target neural network. Local neural network is constantly updated. So the weights of these, the local neural network are constantly updated for every epoch. For every mini batch, but then the weights of your target neural network are held constant for a while. Let's say for some 10,000 time steps or something, it is held constant because it does not move. We do not want it to move. We want it to be constant, and it is constant. And after 10,000 time steps, all of these updated weights can be copied into your neural network 2, and then you can again start from scratch. So this concept of having two neural networks, one is to calculate the local Q value and one more to calculate your target Q value, where the target neural network is not updated and it's held constant for a long time. This concept is called as fixed Q targets. So that is what is explained over here. Let me just get back to my program to see how it's implemented. In our program, it is implemented slightly differently. So what happens in our program is it works on something called as soft update. So what soft update does is the weights of the target is updated with weights of the local plus with a lot of portion of weight of the target and very little portion of weight of the local. So what did I tell over here? I told you that okay. I'm sorry. Yeah, what did I? We have two neural networks, NN1 and NN2, and for a long time, we will, for around 10,000 time steps or so on, we will keep NN2 constant, and after 10,000 time steps, we will update the weights of NN1 with NN2. So this is what I told. But then there is another approach to it. You have NN1 and NN2. NN2 will be updated with a huge portion of NN2 itself. Maybe say, let's say 0.98 or something, and a small portion of NN1. A small portion of NN1 is used to update NN2, and a huge portion of NN2 itself is used to update NN2. So this concept over here is called as fixed Q target, and it is a soft update concept over here which is being used. Any questions on these two topics that you have? Like either experience buffer or fixed Q targets. Shall we move to the next concept, next part?
This fixed Q like teacher disciple. So disciple is keeping score, but teacher is keeping another overall score.
Yes, that's right. Okay. We define our Q network. Q network is a very simple network that we have defined. The input to the Q network will be your state size. In our card pull example, state is a vector of 4. So this will be a vector of 4. And the output is your action size. Action is a vector of 2. So this will discrete values. It will be vector of 2. And there is a ReLU activation in between states, and we just get the output as it is. It is a simple ANN that's being built over here. And some of the hyperparameters have been defined. You have a learning rate. Tau. Tau is the value that was used for soft update. Soft update for, in the case of fixed Q values, there is a mini batch size, and this is the discount factor that you have. And you have your, when you are creating an agent, I told you that you will have two networks which are exactly the same. You have your local network and you have your target network. Both are coming from the same network. It will have the same architecture and same set of weights when you start off. So it's same Q network for local and target. So this was our Q network class over here. So it's the same local and target with an Adam optimizer. And you also define your replay buffer size with the buffer size which was predefined. So when you have to make a step, you keep adding all the new experiences into memory, and only when the memory is got something greater than the batch size, we will get values out of the memory, and you will do what is called as a learn. So during training, this act is going to get us the action that we want. So you pass on the state into your neural network, and based on the epsilon greedy policy, you will be getting an action. So what is the epsilon greedy policy? It is, as I explained before, it is a right combination between exploration and exploitation. Initially, it will return random, which means it will just randomly return some action. Otherwise, it's going to give you an np.argmax, which is nothing but it will give you the best action in the next state. So with an epsilon greedy policy, we either get a best action in the next state, or it is the random action. And with learn is where our loss function comes into picture. You calculate what is the Q target next and what is the Q target value that you have. Based on this, you calculate what is your Q expected, and your loss function will be Q expected minus Q target. So this entire thing that you see over here is an implementation of this formula. So this will be your loss function, or just a minute, I think that was in the previous answer. Yeah, the loss function that you have over here is the current value minus the expected value whole square. So that is your mean square error loss, and that is the loss function that we have over here to calculate. So mean square error loss of what was Q expected minus your Q target, and the rest are pretty straightforward. If you're familiar with deep learning, you just do a zero grad to wipe out all the gradients, and a backward and an optimizer dot step. So basically, designing a Q learning algorithm, DQN, deep Q learning algorithm, needs all of these parts. You define your network over here. This is the network that was defined over here, and you have an agent. This is the agent that we are trying to train. This agent will have a step. Step would mean what is once you perform an action, what is the next state that you land into? That is your step function. Act is what is the action that you're going to take? What is the action? The policy, the epsilon greedy policy is what will be defined in the act function. And finally, you will have your learn function, where you will calculate the loss, and you will do you will compute the loss, and you will do the back propagation. So this is where that is happening. And you have to define your replay buffer, which we discussed earlier. This has two simple functions: add into the experience replay buffer, and stack a sample. Sample is to randomly sample from your replay buffer. And once all of these things have been created, you create your agent. So if you remember, our state size is 4 and our action size is 2. And once you do this, this is your training part. So training part is get the states and pass it into that, and you will get your rewards. Just append all of those rewards. So this is any normal training algorithm that you have. I will get back to this function once again. It's like I've been giving a lot of information, so I just want you to digest and look into the program once. I will repeat the training part once again, but just to tell you how it goes, I have trained it for 2000 episodes. Initially, you can look at the reward that it got. So initially, it was just able to balance for some 18 steps, 14 steps, and 10 steps, and so on. But as you go further, it was able to do a better job, and it was able to get more than 180, 190 time steps. It was able to balance this correctly. And you can see that it has steadily the reward. So our environment was defined like this, wherein for every time step that you balance it, you will get a 1 reward. So this means that it was able to successfully balance it for 196 seconds or 196 time steps. And the reward is significantly increased. So the agent is learned how to train. And then once you run these two things, you will be able to make out the difference for yourself. When you run this, this will take some 3 to 4 minutes to load, but then do run this and you will know that. So see, over here, I am doing it for 5 episodes, which means 5 times. So for 5 times, it will balance it for 200 time steps. So it might fall off, but even if it falls off, it will again come. So you can change this to 1 or something, or 2 or whatever you want. Even 5 is good. But then once you run this, you will be able to see that, you will be able to see on the video that it has learned how to balance it compared to our random policy that we just had. We just had a random policy over here where it was not able to balance and it would fall off in some 15-20 steps. But in this video, you can see that it is able to balance up to some 190 steps and above. I will pause here for a minute to give you some time to understand the program and go through it slowly. In the meanwhile, you can also make sure that you set the kernel to PyTorch 1.9 and you can just say restart kernel and run all cells. Once you run all the cells, you can see the 2 videos will be uploaded. So you can see the 2 videos, first with a random policy and finally with a trained policy. Please do run this program to understand how this works. And once you run it, if you have any questions, you
what
want
is
me
that?
to go. Yeah, yes.
Ma'am, why are we using 1.9? Why can't we use 3? PyTorch 3? Ma'am?
The available kernels currently is this over here. So, Python 3. I am using PyTorch. I have in PyTorch 1.9. All of the PyTorch modules have been pip installed. So I would prefer PyTorch 1.9. So what I would request everyone to do is change the kernel and do a kernel restart and run all cells, run all the cells and play in the 2 videos to understand how the algorithm has trained the environment. And also, I would like to hear from you if all of you have been able to run this program successfully. So please do let me know if you're able to run and if you were able to see the output. Any questions any of you have? I can try to answer them.
Hello. Yeah.
Yes.
So can you talk about the discount code, gamma factor?
Discount factor. Yes, sure.
Discount
Just give
factor.
me. Okay. Yeah. Sure. So how this works is, just give me. You have what is called as a policy. Okay, this policy will be this policy is what has been defined. So policy is nothing but at any given state, what is the action that you're supposed to take. If I tell this to you, this is called as a policy. I have states S1, S2, S3. If you say in this state, go up, go right, go left or something like that, this mapping between state and action is called as a policy. This can be straightforward like this, or sometimes it will be also be probabilistic, which means in state S1, I will tell you with a 0.8 probability go up and with a 0.2 probability go down. Okay. So this is the policy that I have, and using this policy, you will perform some kind of an action. And you will follow the same policy to continue for a long time. Okay. So let's say I'm in state S1, I do some action up or something, and then I go to state S2. Over here, I get a reward R, and from here, you again perform some other action down or whatever, and you go to state S3. Here also you get, let me call this as R1. I will get another reward R2 and so on. So you are going to get a lot of reward as you implement this policy and go down the line. So when you're calculating the Q value, it goes like this. The reward that you get plus the Q value at the next state, okay, by following a policy, the Q value at the next state. What is the Q value at the next state? Q value at the next state is the reward, let me call this R1, the reward that you get in that current state plus Q value at the next state. So this goes on and on. The reward that you get plus Q value in the next state, if you dig deeper and try to see what is the Q value of the next state, there you will get another reward R2 and the Q value that you get at the current state. So basically the total expected will be the reward that you get at this state plus the reward that you get at the next state and the reward that you get at the next state and so on. Now, when this is the scenario for I am in this state S1, I want to take an action A. When I want to take an action A in this current state, what should influence this action? What should influence this action? I want to decide. So I'll just give an analogy over here so that it helps you understand better. Let's say I am studying in first standard, okay? When I'm studying in first standard, my parents tell me that if I pass the final exam with good grades, I'm going to get, they will let's say they'll buy me a toy for some 1,000 rupees or something. Okay, this is what they tell me. And they tell me in second standard, also if I pass, remember I'm still studying in first standard, okay? I'm still in first standard. They tell me that if you pass final exam, you will get a toy for 1,000 rupees. In second standard, also if you pass the final exam, you will get a toy for 1,000 rupees and so on. And if you finish your 10th standard also well and you get good marks, again we will buy you a toy for 10,000 rupees. Okay, this is what my parents tell me, but remember I'm still in first standard. So what I do on first standard will be highly related with this reward, and really 10th standard is really far away. So I need to discount the reward that I get in 10th standard. So I really don't know, no, at that time 10,000 might be worth it or not worth it, or I might not be really interested. I don't know, a lot of things might happen in 10 years. So what I will do is, I will say the reward that I get in first standard plus gamma times the reward that I get in second standard, plus gamma square times the reward that I get in third standard, and so on. So this is how I define my system, where gamma is a fraction. It'll take a value between 0 and 1.0. So we know that fractions, when you have fractions and you multiply a reward with a fraction, you'll get a lower number. And when you square that fraction, it's going to be an even lower number. So this will be, let's say gamma is 0.5. So this will be 0.5 times R2. This will be 0.25 times R3, because I'm discounting third standard even more, because I don't know what will happen in 3 years. So we introduce this concept of discounting to discount the future rewards. The current reward, I know that I will get it immediately, but the future reward, I'm not really very sure. My parents might forget. I don't know what's going to happen. So I do not want to rely on those rewards a lot. I only want to rely a lot on the current reward. I do not want to rely on those rewards, but still they are important. So what I'll do is I will discount those rewards. So as you go further and further, you will increase the power of gamma. So it is going to become an even more smaller and smaller number. So if you're going for a long time in time, then it will be a very small number. So you get to choose. It is a hyperparameter over here, gamma, between 0 and 1.0. So you have to choose what should be your value of gamma.
Yeah, I got it. Thank you.
It's like salary versus stock option. Employees want current salary. Who cares about future options, which will vest after 4 years? That's what it. So we discount future options rewards. We are more interested in more cash component in the salary at the moment.
Yes. Thank you.
Excuse me, I had a question.
Yes, sure.
Yeah. So could you go to the IPython notebook once?
Yes, sure.
Yeah, out here in the score versus episode plot, like
Correct.
I wasn't able to understand one thing.
Okay. Okay, what we'll do is I just have a scores and I also have a score window. So all of these, what we are really interested is this reward. The reward is what you take an action. So the environment.step means environment executes this action and you get a reward. Okay. So, and when you say agent.step of reward, this reward will be used by this agent to calculate loss, to calculate Q values and do all of the back propagation. But then the score that I have, I am just maintaining it to print this graph. So what exactly happens here is I start with episodes. For every episode that I have, the score, I will reset it to 0 and I keep appending the scores, and I have something called as a scores window, because the scores window, I think it it has a maximum length of 100. So what happens is it just sums up the scores of the last 100 times, and I just give the average of those scores. So these two things over here, scores and score window, they are used just for this visualization, just to plot the graph over here to tell me what is the average score. So this average score is the average over 100 scores. It's the average over last 100 times what you played. So that is average score that I have, that is used to calculate and plot the graph. But then the real training happens with the reward that you got. How do you get this reward? You do an environment.step of action. And when you do an environment.step of action, here, see, if you look at gym's environment, we are creating a gym environment. So when you create a gym's environment, I will just scroll down. Yeah, you have your step function here, environment.step, it takes action. So when you do that, I'll just scroll down. It gives you the state and it gives you a reward. So whatever reward was defined in your gym environment, it will calculate that, like if you just fall off, it will just give you fell down and it gives a reward of 1. Otherwise, if you don't fall off, it will keep adding the reward on and on and on, and it gives you a reward. So when you say environment.step, it calculates the reward and it gives you that reward. So that is the reward that you get. And this is what is used in calculation of Q value and also our loss function. But score and score windows just for display purposes that we have here. Now, I hope that answers your question.
Did we cover exploration versus exploitation?
So Vivek, that was a part of module 5 basically. So I gave a gist of how that works, but mathematically, no.
No, just an example that when I moved to Bengaluru and did not want to try certain kind of restaurants, let's say certain new cuisines, right? But when I did, so I'm exploiting what I already like. I like Thai food and Indian food, so we only go for those. But one fine day, I happened to explore Vietnamese
Yes.
food, and I fell in love with it. So exploitation means going for safe choices which you already know. Exploration means trying new waters and in the hope of finding more satisfactory result. So once I tried Vietnamese food, I realized, oh, I was missing all this time. It's so good, right? Like that. So you in the beginning of the RL training process, you do more exploration. So you explore more possible scenarios where reward could be maximized. But in the later part of RL process, you do more exploitation where you go with safe choices. Same with these IPOs coming in stock
Okay.
market, right? So you want to explore the IPOs coming in stock market. You never know, they may give you better return. But unless you try them, you can't tell. So like that. So you basically, if you are risk taker, you are more explorer. But if you are a safe player, then you go for safe bets. You don't try new things. But then you may not get so many rewards which are possible with new exploration.
Yes, so in code, this exploration and exploitation is handled over here.
Yeah,
I
so
will
at
just
the
show that
1000th
once.
time step, like the reward suddenly the score.
It was, yeah, initially it was, I guess the exploration exploitation based on that you get a greedy policy. It was still exploring, but then once it just most of the time it's able to exploit and then it has learned and it is able to do a better job. So it is a bit gradual and a bit sudden, but yes. So exploration and exploitation in code, I'll just show that to you. Okay, Agents Act, yeah, over here. So this is it is a policy that is defined, which is called as an Epsilon greedy policy. So what happens
Okay.
is you use the
All
Epsilon
right.
greedy
Thank you.
policy over here to pick an action. And if you just take a random number, if it's greater than epsilon, you exploit. Exploit means you get the best value. Otherwise, you do a random dot choice, which means you are still exploring. Initially, what happens is this value will be it will be very high. It will be very high. So when you pick a random value, there is not a probability that this random value is greater than this. So it will always go to the else part and it will explore. But we are gradually decaying the value of epsilon. So when you gradually decay or reduce the value of epsilon, it will more and more favor exploration than exploitation. So this entire concept of exploration exploitation is encompassed in what is called as epsilon greedy policy, and this is the implementation for your epsilon greedy policy. This is covered more in depth in module 5 where we get introduced to Q learning algorithm. Any more questions any of you have?
So everybody was able to run the program and see the cart pole balancing. Is anybody still stuck with running the program? It is running in CellStrat Hub, but one person reported it's also running in Google Colab. We prefer CellStrat Hub, but if you want to run it in Colab, that's fine.
There is some file save error.
But I also got that.
But
We'll check on that.
normally it's working.
But yeah, it's working, right? So even I got that. I will explore that.
Yeah.
Okay. So any other questions, folks? RL is a new area, complex, yes. So you have to spend some time on the RL algorithms and projects. So whole RL pack is there for you in CellStrat Hub. So feel free to try from project number 1 onwards, and you can develop expertise that way. If you want to enroll in the detailed RL course with recorded videos and assignments, so contact CellStrat offline. Any other final questions for today? Okay, so Shubha, are we done?
Yes, Vivek. We are done.
Okay, audience. So thank you all for joining, and look forward to hearing your feedback. Or if you are interested in the RL course, and feel free to keep using CellStrat Hub. As I said in the beginning, don't check out all the packs. Most of you will be on the free tier in CellStrat Hub, and it has 8 GB, and you may run out of space. If you are out of space, contact CellStrat offline through variety of channels, and we'll help you delete some of the packs so that you can have some free space in the free tier. You are welcome to upgrade to premium tiers, which are available, which provide you more space in CellStrat Hub, as well as different other hardware capacity. So thank you all for joining. Thanks a lot, Shubha, for excellent presentation on what remains a very complex topic. Unfortunately, it remains a bit complex topic, and so we have to keep doing these workshops. Okay.
Thank you.
So